What is going on, everybody, and welcome to part 2 of the reinforcement learning series, as well as part 2 of doing Q learning. In this video, we are hopefully going to finish this agent and we will have it traversing up a mountain in no time. So where we left off, we initialized our Q table, but the Q table just has random values, and now we're ready to actually start updating those random values to hopefully meaningful values and having great success getting up this mountain. So the first thing I'm going to do is just kind of clean up these print statements. We don't need them here, and they're just kind of creating clutter. Now I'm going to add in a couple of constants. The first one's going to be learning rate, and we're going to say 0.1 here. This would be anything from 0 to 1. Now 0.1 is kind of low, but you might actually decay a learning rate here, just like you might with your typical deep learning applications. For now, we're just going to keep 0.1, keep it nice and simple, no decay for that. The next thing we're going to do is we're going to add a discount, and this will be 0.95. Now the discount is kind of like a weight. It's a measure of how important do we find future actions. So in this case, we're going to say 0.95, and you'll see in a little bit when we actually start to write our new Q variable function, or algorithm, whatever you want to call it, how discount comes into play there. But basically it's a measure of how important are future actions over current actions, basically, or future reward versus current reward. Because the way the agent works is it's always going to go off of the max Q value. Well, if your max Q value is always looking ahead to future max Q values as well, that's going to back propagate all the way down a long chain. It's basically 0.95 times 0.95 times 0.95, so that's going to go on a long way down a chain. So anyways, it's a measure of how much we value future reward over current reward, and it's a value between 0 and 1. So let's discount. We're also going to throw in episodes, and we're going to say we'll have 25,000 episodes. We need quite a few episodes for this agent to learn, but don't worry, 25,000 episodes doesn't actually take that long, as long as we're not rendering every single one of them. So now we have our Q table. Now the thing that we need next is the env.reset, as well as the action here when we take a step. That returns to us these states, but the states are these continuous states, and like I was saying before, we need to actually convert those continuous states to discrete states. So we need a quick helper function that's going to help us do that. So we're going to say define get discrete state, and we do that by passing a state, and then we're going to say the discrete underscore state is equal to the current state minus the environment dot it's the observation space dot low divided by the discrete observation space window size. Then we want to return this in tuple form, so we're going to return a tuple form of that new discrete state dot as type, and we're going to make it a numpy int. So this will give us a nice discrete state. And the first way we can test that really quickly is actually I'm going to take this env.reset from up above, and I'm going to cut it, and I'm going to paste it actually down a little bit here. And we're going to start off our discrete state as being equal to get discrete state env.reset. So even though the env.step returns 4 values, env.reset just returns the initial state to us. So yeah. So we can just pass it right into there. All right. So now I can print discrete state, save that, we can run that, and we can see that starting discrete state is a 7 and 10. And then what we can do is we can actually look up that discrete state. So for example, we could say Q table, and because it's a tuple, we can actually index by tuple. So, you could index, you could say 7 or something, but we can actually pass the discrete state itself. And let's go ahead and print that. Copy, paste. And you can see here, these are our Q values, our starting Q values. So they're just random and meaningless. But if we wanted to go off of the maximum one, we would just say np.argmax Q table here, paste, and we see the argmax was actually the 0th. So we want to go with action 0. So, okay, pretty cool. So that's how we get the max value. So now what I'm going to do is just kind of clear these out. And cool. So now we're ready with this new discrete state. We can actually take our first action and then slowly start to generate new Q values. So I'm going to actually uncomment out this looping down here. We still want to we're going to start with done equals false. And then now, rather than action being hard-coded as a 2, we're going to say action equals, I shouldn't have deleted that other value, but whatever, np.argmax Q table, and then we index it by that starting discrete state, but later it's going to get changed. So we'll get a new discrete state soon enough. But for now, we have our action. Then, new state, reward, done, blah, 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 still is an action. And then we also want to get our new discrete state. We want to get that new discrete state because we're actually going to use that in our formulation of the Q values. So we get the new discrete state as being get discrete state for the new state. We don't any longer need to print those rewards, but here we can do the render, and then we're going to say if not done, because the environment might actually be over. So if it's over, we don't want to do anything. But if it's not over, so if not done, first we want to say max future Q is equal to np.max, not argmax, but max, because in this case we're going to use max future Q in our new Q formula. So we actually want that Q value rather than what's the argmax. So we're going to say np.max Q table, and then we just index that Q table by new discrete state. And this max future Q soon we will multiply that discount to the max future Q, and that's why we're gathering this. And that's how slowly over time future actions get back in their rewards. Not really reward, like the reward gets back propagated, but really it's the Q value gets back propagated down the table. So this is really where all the magic happens. Anyway, max future Q, we get that max value. We also want to grab the current Q value, so that's just going to be Q table. And in this case, we can slice it by doing new Q table, the current discrete state, yeah, and then plus the action. So we just kind of add this little tuple to this. So we're slicing it by this state here, the discrete state, which is a tuple. So this is, let's say a 20 by 20, and then the action. So we're getting the exact Q value. So as opposed to if we just did discrete state, we would get 3 values. In this case, we're just getting the Q value. So we get the current Q, and now comes the actual Q formula, which will be equal to, and this is what this is, and hopefully this is the last time you ever have to look at this again. Anyway, that is going to be equal to 1 minus the learning rate. I don't know why it didn't, why it doesn't want to autocomplete for me. Maybe because I don't know. Anyway, 1 minus the learning rate, and then times whatever the current Q value is plus the learning rate times the reward that we got, reward, plus the discount times the max future Q. So this is the formula for calculating all Q values, And the way it back propagates is based pretty much purely on these values here, where yes, we do get a reward for things, but we really only actually get a reward ever for completing this entire thing. Otherwise, the reward is always a -1. So really, it's only once we finally get a future queue that finally things will start to back propagate, and kind of, you know, you'll get one completion, and then after you get the one completion, you're more likely to see another completion, and then that just kind of snowball effects basically. So anyway, there's our new queue. And then once we have the new queue value, we just need to update our queue table with that new queue value. So we would just say queue table for that discrete state plus the action that we took. Now we want to update that as with the new queue value. So just take note and pay, I guess, close attention that we're updating the discrete state after we took the step of that discrete state. Okay, so we took the step, we've received reward for this thing already, we have this new state, but based on this new state that we got and the reward and all that, we are now going to update that action that we just took. So as a, you know, discrete state as opposed to using the new discrete state, let's say. Okay, so if not done, that's what we do. But if we are done, the environment, either we took 200 steps and we just suck and we didn't get anywhere, but we might elif new underscore state 0. So we have position and we have velocity. If that is greater than or equal to the environment.goal underscore position, then what we want to say is queue table and then discrete state plus the action. We want to set that value to be 0. And so that's our reward for completing things. You know, just nothing. Just no punishment. You're welcome. And then that's basically it. So then we just discrete state equals new discrete state, and the loop goes on and on and on. So with that, let me go ahead and run QLearning 2, and let's just make sure we don't have any errors up to this point. Isn't he cute? He's so cute. Okay, now that we've done that, we actually want to iterate over episodes. So this only runs one time, and that's not really useful. So now we would want to say, basically here, for episode in range episodes, we want to do this. Cool. So then we should add something to the tippity top where we kind of display some metrics. Now, I think probably in the next tutorial we'll dive a little deeper, but at least to start, it would be useful to know sort of where we are from time to time. So I'm going to add another metric called show underscore every, and we'll say 2,000. So every 2,000 episodes, just like let us know that you're still alive and you're doing things. So for episode and episodes, if yeah, so we'll just say if episode modulo show every 0. So basically, if we can divide the episode number by 2,000 and the remainder is 0, then what we want to say is we'll say render equals true. Else we'll say render equals false. Also, let's just print episode, and then we'll come down to where we render, and we'll say if render, then render. And And this is because actually rendering the environment is really slow. Otherwise, we can actually run through these environments really, really quickly. So, I closed it. Let's, okay, Q learning 2. Let's go ahead and run that real quick, see what we get. So this is our starting environment, not very good. And then we'll continue running through, and I'm not going to go all the way, but we'll just kind of go some distance for now. Why this didn't disappear? I guess maybe once we get to 2,000 steps or episodes. Also, that's just running really slow. I would have figured we would have 2,000 episodes by now. Anyway, yeah, he's already getting better. I was expecting to have to show you one more likely parameter that you would almost have to have, but he might actually succeed. I wonder if we just got lucky. Also, we should have been printing if we reached our objective, and we didn't do that. Yeah, wow, by 4,000 steps, he's already made it. So now what I want to show you guys, let's go back. I've got a few things I must show you, even though we've already solved the thing. This is just such a simple objective. Let's print an F string, and we'll say we made it on episode, and then we'll just pass episode. So let's save that, rerun that, and let that start to run. We'll kind of see how long it takes to start getting some victories here. Cool. And while we wait, shouts out to some of my wow, they already made it. Oh, he's killing it. He's already made it by 100 episodes. He's making it every episode. Incredible. This is actually news to me. And then by episode 2000, he should solve it. Ooh, it looked like he was solving it every episode. I wonder why he's actually not solving it anymore. Is that not every? It looks like it's every episode. 1, 2, 3, 4. It sure looks like every episode to me. Let's see what happens on episode 4000. Recent members, I will get back to you in a moment. This is so fascinating. I can't believe he's already made. Oh my goodness. So every time I guess he's going to make it. Now the question is he always going to take that long? Because I'm not sure you actually have to swing up and back and then up and back again every time. Curious. Very curious. Like if he just swung up, back, and like I think that you could make it quicker. Anyway, back to my most recent channel members. Brand new members, Sir Sroka, the Dragon 573, Jesse Stillwell, and Kyle Gumby. Thank you all very much for your support. Welcome to the club of amazing people. So it looks like that time it did go a little quicker. And the quicker you go, because it's a -1 every time, every frame. So if you could find a quicker way to achieve the objective, that would be superior. Oh, he almost makes it, but nah. Okay, so very interesting. I didn't think that that was going to make it by episode 200. Let me just try that one more time, see if he makes it again by episode, what was that, 200 or 300, I think? I mean, it was so fast. It was so fast that it was solving this environment. Yeah, 200! Oh my gosh, and then you can see, like, it takes a little bit, and then once he starts finding it, it's like, and it just, like, snowballs in. And then soon, it's like every episode he makes it. Pretty cool, actually, how quickly that worked. I'm kind of surprised. Yeah, he's already really good. Okay, so this is actually strange that he was able to make it that quick, because we actually need one more thing usually, and it's called epsilon, and it's a random, it's a measure of how much randomness you want to do, or how much exploration you want to do. Because I don't want to talk about this in the next video, I'm just going to slap it on, even though we somehow achieved this objective that quickly. What I'm going to do is, what? Hopefully not that. Okay, so we're going to add a couple, so we're going to say epsilon, and we're going to say that is equal to, I guess I'm going to start at 0.5. I'm just going to start it kind of small. And this is going to be the chance. So again, epsilon would be between 0 and 1. The higher the epsilon, the more likely we are to just perform a random action, an exploratory, which is just fancy for random. And then over time, what we want to do is we want that model to stop exploring. So even though our model has actually solved this, I believe, I can't remember, I think if you just go up a little bit and then swing back as quickly as possible, I think you can achieve the objective a little quicker. And it is, in this case, more advantageous to solve it quicker. But once this model has figured out one way to possibly do it, it's never gonna come back. So to start off, I'm thinking we'll have some randomness here, and then some environments will just simply require random actions to be taken to even be solved once. And then also some things you like, ways to solve something you would never think of, the agent can find out because you've allowed it to do these exploratory moves. Anyway, enough. And then, so we'll say we'll start at 0.5, then we'll say start epsilon underscore decaying. This is actually kind of curious. We're going to play with this, I think, in a future episode. Anyway, end epsilon. Nope, I said, you jerk. How did... Stop it. End. Why are you... Oh, that's how you're going to... Okay. End epsilon. I don't know about that. I'm not sure about that level of autocomplete. It's like, well, it has an E, an N, and a D in it. I'm going to say episodes divided by 2, and the double div is like Python 2 type division, right, where it will always divide out to an integer, so we don't have a float. Okay, so now what we're going to say is the amount that we want to decay by each episode, we're going to say is epsilon underscore decay underscore value equals epsilon. I hope this video is not like an hour long already. Anyway, end epsilon decaying minus start. What? You don't want to, okay, you don't want to autocomplete that because it was touching subtraction. Anyways, epsilon decay value. Great. Okay, now we're going to go down to the very bottom after the discrete state update and then just one tab over, so a per episode update. What we want to ask is if end epsilon decaying is greater than or equal to the current episode that we're on, but it's also, and the episode is greater than or equal to the start epsilon decaying. If that's the case, we're going to say epsilon minus equals epsilon decay value. Save that and we'll run that, and something tells me it's probably not going to learn all that great. But now I'm super curious. I'm going to have such a hard time waiting to the next video that I probably won't even wait. Like, part of me wants to like start the decay on episode 2000. Like, once he's already solved the environment, then be like, all right, now take a lot of random actions and then see, does he learn to solve the environment like way quicker? See, I feel like that's super inefficient. I feel like he could go just barely up and then go back and then be good. And I think that's kind of what we're hoping epsilon could get us to. I just don't think it's going to happen, unfortunately. You almost need, maybe we do need a really high starting epsilon. I don't know. Anyway, I think that's probably something we should focus on the next tutorial, because this one's probably super long. See how inefficient that was? If he was allowed to have continued, he would have made it to the flag. He understood. Yes, it's a he. He understood how to get to the flag, It's just he didn't have enough time. We cut him off because we're jerks. But he would have made it. I'm just going to look at a couple more. You guys are free to leave anytime. Don't you? I really think maybe if it goes up, I don't know. Maybe this is as efficient as it could possibly be. I don't know. Anyway, that's all for now. Questions, comments, concerns, whatever, leave them below. Come hang out with us in discord.gg/Centex. If you want to support the content, you know the deal. That beautiful blue button. It's calling your name. It's begging. Cool. Yeah. In the next tutorial, we'll talk about how to do some more stuff. Like, this is one very, very basic way to debug what's going on. But in the next tutorial, we'll talk about how to start kind of generating our own metrics that we can kind of start looking at. Because I think time to completion and oh, that was so wonderful. That was the most efficient solution yet. Hold on, everybody. Hold on. I think I saw what I was talking about, what I really wanted to see. That was so perfect. I hope I didn't miss him like swinging back and y'all are like, what is he talking about? Oh, like I think that's what he did the first time. He like just barely swung back the perfect amount. Oh, that looked so good. Now I'm going to have to go back to the video and see if it actually did that. Because that's the perfect solution right there. Ah, man. I'm spending way too long. I'm way too excited about this mountain car thing. It's so cool. And I'm such a nerd. Okay. Till next time. Alright, quick and unfortunate update. Totally forgot, like, we calculated epsilon, we decayed epsilon, but we never actually used epsilon, and I don't want to have to talk about this in the next video, because we're actually just supposed to be analyzing things, so I'm going to fix that. So, where we actually decide on our action, this is where we actually want to decide whether or not to use epsilon. So, what we're going to say is if np.random.random, this creates a random float between 0 and 1. If that is greater than whatever our epsilon value is, as long as that's greater, we want to actually do actions in the usual way. Otherwise, we actually just want to do a random action. So we're going to say action equals np.random.randint, and we want that randint between 0 and env.action space and then the number of actions. So now if we do that, and I set epsilon, well, we can leave it at 0.5 and it probably won't learn as quickly. So let's just rerun this real quick. Hopefully we don't see it's learning by episode 200 anymore. And we also, I'll make sure it at least learns, but at this point, like, this is kind of where you want to start tinkering with these various values. So, okay, so it starts learning at more like episode 1200 or so. And the benefit here is that we're actually still doing some exploration, because as soon as it finds one way to the flag, it's just going to like super optimize very quickly for that way of getting to the flag, when there might be a better, more efficient way to get to the flag. But as long as it's found it one time without any exploration, without any randomness, it's always just going to kind of optimize that one path. And for many tasks, maybe that's okay with you. But in the case of like the mountain car, for example, like that, what we just watched was like super inefficient. So the goal is to make it efficiently. Anyways, we'll talk more about kind of tinkering with values and statistics and stuff in the next tutorial, but just had to make that change. So I'll see you there.